is conservation laws. And conservation in science means values that don't change over time. So it means it doesn't change over time. So for example, conservation of energy means the total amount of energy in the universe is the same at one time as it is at a later time. The two things that we're going to talk about are first, conservation of linear momentum. And what you need to know about this, conservation of linear momentum, first of all, is useful in problems involving collisions. And the second thing to know about this is we're going to do a very brief discussion of this. So we'll cover this very briefly. And then we're going to go on to the one that we're going to talk about more than conservation of linear momentum. And that is conservation of mechanical energy. And conservation of mechanical energy is a special case of conservation of energy. It's not really the same thing as saying that all the energy in the universe stays the same. But for some cases, we can reduce the total conservation of energy down to conservation of what we're going to call mechanical energy, a subset of the types of energy that there are. This is a special case of conservation of energy. By the way, the special case that we're going to consider, like some of the things that we're going to ignore, are things like changes in temperature, transfer of thermal energy from one body to another. We're not going to consider molecular energy. We're not going to consider chemical reactions. Those are all ways that energy can be stored and used. We're not going to deal with that. We're going to deal with, so conservation of mechanical energy is useful in cases where there are not big temperature changes. You just have things flying around, bouncing off things, balls being thrown through the air, that sort of thing. Okay, so first I'm going to talk about conservation of linear momentum. And conservation of linear momentum, like I said, if a problem has a collision in it, involves a collision, this is probably the way to go. Probably the best approach. if there's no collision, it's probably the wrong approach. So it's pretty easy to tell when this is useful and when it isn't. Conservation of linear momentum says that under certain conditions, this property called linear momentum is conserved. So at one instant, the linear momentum is the same as at a later instant. So let's first talk about what linear momentum is. We need to know how to calculate that. The linear momentum of an object is always going to be denoted with a lowercase p. I'm not sure where that comes from, but I would guess Latin something. And the linear momentum p is equal to the mass of the object times the velocity vector of the object. There are a couple of things to notice about this. The first one is that this is a vector property, so it has direction. So P is a vector. And that means that linear momentum has a magnitude and a direction. And the second thing to notice about it is that the magnitude of the linear momentum tells you something about how hard it would be to stop an object. So it tells something about how hard the object would be to stop. Okay, so let's think about, to make sense out of this number 2, let's think about two things moving at 10 meters per second, okay? One is a baseball, like just being lobbed through the air at 10 meters per second, and the other one is a train, okay? So a baseball has a mass of 0.1 kilograms. Multiply 0.1 kilograms times 10 meters per second, and you get a, in SI units, you get a linear momentum of 1. And I'll write the units down in a second. It's kilogram meters per second. Okay, so that is a momentum magnitude of 1. And that tells you something, you know, baseball is pretty easy to stop. A train has a mass of, let's say, 50,000 kilograms. Okay? It's also moving at 10 meters per second. The velocities don't tell you anything about how hard the two things are going to be to stop. According to velocities, those two are equal. They each have a velocity of 10 meters per second. But the train's momentum is 50,000 times 10. So the momentum is 500,000 times as big as the momentum of the baseball. And what that tells you is you want to let it go by. Catch the baseball and let the train go by, you know? I don't know if you knew that, but I think that's, I'm a little nervous. That's why the class is so small. Not really. Okay, and then units. Yeah. Yeah, so you would, um, not, it would never happen immediately. It would happen over some amount of time. But yeah, that's the kind of thing that you would calculate in a collision. Yeah. Um, so the units for linear momentum, well, it has to be units of mass times units of velocity. So that would be, so it has to be units of mass times a unit of length divided by a unit of time. And in SI units, that means kilogram meters per second. Okay, so conservation of linear momentum. Says choose a system of objects that experience no outside forces in your chosen coordinate system. Well, I should say net, actually. You can have a bunch of forces as long as they add up to 0. Then the linear momentum, the sum of the linear momentums of the different objects at instant 1 has to be equal to the sum of the linear momentums at instant 2. Okay, so let me do an example. So let's take a top-down view of this problem. And let's say you have a train car with a mass of 2,000 kilograms that's moving at 3 meters per second. And it collides with a train car that has a mass of 4,000 kilograms. That's at rest. If after the collision, the 4,000 kilogram train car is moving to the right at 2 meters per second, what's the velocity vector of the 2,000 kilogram car after the collision? Okay, the first thing we have to do is choose a coordinate system. We want to choose one where, you can't always do this, but in this kind of problems, you always can. You want to choose a coordinate system where there are no net forces acting. And this view works fine. So I'll choose a coordinate system like this. There is, on each one of these, there's a weight force going down and a normal force going up. Those are equal and opposite, and they're not in this plane anyways. Besides that, there are no net forces acting. So conservation of linear momentum is going to work here. So now let's add it up. At instant 1, that's going to be before the collision. The linear momentum of the 2,000 kilogram cart is going to be the mass, 2,000 kilograms, times its velocity vector before the collision. What would that be as a vector? It has a magnitude of 3 meters per second. 30, yep. And the linear momentum of the 4,000 kilogram train car is 4,000. What's its velocity vector? Yep, 0, 0. And so the 2,000 has momentum of 6,000, 0. That's in kilogram meters per second. And the 4,000 has a linear momentum of 0. And now, what do we know after the collision? So at instant 2, after the collision, the linear momentum of the 4,000 kilogram train car is its mass, 4,000, times what velocity vector? Yep, 2 in the positive x direction, so 2, 0. So this is positive 8,000, 0. And what about the 2,000 kilogram train car? What's its linear momentum? It has a mass of 2,000, and we don't know the velocity vector, so I'm going to just write that as like Vx, Vy. And so you could simplify this if you want right now to 2,000 Vx, 2,000 Vy. And now plug that into conservation of linear momentum. And it says 6,000, 0. So the left side is what I'm using before the collision, plus 0, 0 is equal to the sum of these after the collision. So 8,000, 0 plus 2,000 Vx, 2,000 Vy. You have two equations there. The x equation says 6,000 is equal to 8,000 plus 2,000 Vx. Solve for Vx, and you get -1. The y equation says 0 is equal to 2,000 Vy. So Vy is equal to 0. And so the velocity of the 2,000 kilogram train car after the collision is -1 for the x component, 0 for the y component. Any questions about that? Yeah, so right, it bounces off and goes backwards and knocks the other one forward. That doesn't always happen. It depends on the masses and what their velocities are before. There are cases where they both go in the same direction, cases where they never both go backwards, I guess. There are cases, you know, the like sharper image toys with the balls that hang there. It's called like Newton's Cradle or something. So the stainless steel balls are hanging on strings. You take one off, let it go. It hits the first one. All of these stay at rest, and the one at the other end pops out, and then it comes back. It's sort of cool. That's a case of collision where what's going on is this one comes in with some velocity, hits this one stops dead, and this one takes off with the same velocity this one had before. And you can do that calculation using this. One important thing to notice about this is knowing the masses and velocities before the collision is not sufficient. So before the collision is not sufficient to calculate the velocities after the collision. I mean, that's sort of what we just did in this example problem, but notice that in the example problem, we started with we had additional information besides just the velocities and the masses before. We also had to know something about the 4,000 kilogram train car after the collision. Okay. And if you think about the way collisions work, it makes sense that that would be the case. So imagine someone says, here are two spherical objects, and they come towards each other at 50 miles per hour each, and we know the masses. What are going to be their velocities after they slam into each other? And the answer is there's not enough information. You need to know what those spheres are made out of. If those spheres are made out of wet tissue paper, they'll just slump together and fall down on the ground, right? If they're super balls, they'll bounce off each other and go in opposite directions. So the masses and those starting velocities are not enough to know what's going to happen after. You have to have some information about the nature of the collision. And that's when I gave that extra bit of information, the velocity of the 4,000 kilogram train car after the collision, that was enough information about the nature of the collision to fill out the rest of what we didn't know. Yes. Then there are infinitely many answers. That's right. Right. We have to know something about the collision. So you have to know something about the collision. You are going to do very few problems like this, but yes. And if you ever see if someone ever asks you about something where you're not given any additional information, just know mathematically there's nothing you can do. It's not about like whether you're good or bad enough at physics to do it. You know, it's just not enough information. So you have to know something about the collision. So there is one type of collision that I want to talk about. That's the simplest type. What? This is the case of so what if the train slammed it, like when trains slam together, usually hopefully they're doing it with the plan of linking together, you know. So you know, we calculated that those trains hit each other and then one bounced off and one went that way. Well, that's one possibility of what would happen if they didn't link. But what if they did link? You know, then the answer that we calculated isn't possible, because whatever the velocity of one is has to be the velocity of the other one. So that's the simplest case. It's called inelastic. And in inelastic problems, inelastic collisions, the two objects have the same velocity after the collision. They move as a single object. So the objects have the same velocity, same velocities after the collision. Each other after the collision. Okay, so let's do an example like this. Okay, so let's say that there's a kid on a skateboard. And he's trying to catch this ball. That's coming towards him with a velocity of 5 meters per second. And let's say that the kid and the skateboard have a mass of 20 kilograms, and the ball has a mass of 1 kilogram. And the kid's at rest when he catches the ball. And we want to know, once the kid catches the ball, what's the combined velocity, what's the combined velocity of the ball and the kid? So at this point, they're one thing. They have to have the same velocities. Okay, well, the first thing we have to do is choose a view where there's no net force acting. The view that I've drawn here, there's a weight acting on the ball that isn't counteracted by any normal force or anything. So it's always a safe bet to take a top-down view. So that's what I'm going to do. So here's the ball coming in at 5 meters per second. Here's the kid from above. And I'll use a coordinate system like this. Okay, so conservation of linear momentum says add up the momentums of the objects before the collision. So we'll do the ball first. What's the mass of the ball? Yep, 1. What's the velocity of the ball? 5 in the positive x direction, so 5, 0. What's the mass of the kid? 20. What's the velocity of the kid before the collision? He's just standing there, so 0. And then after the collision, he catches the ball, and now we can think of that as just a single object with a mass of 21 kilograms. So now we can write this as 21 kilograms with whatever the combined velocity is. I'll just call that Vx, Vy. We can calculate both of those components. The x equation says 1 times 5 plus 20 times 0 is equal to 21 Vx. And can someone calculate Vx? .2 meters per second. That seems right. That's right, isn't it? Yeah. Oh, by 5. Oh, I see. Yeah, right. Yes, exactly. Yeah, it has to be something small. 2, 3, 8. Okay. And then the y equation says 0 plus 0 is equal to 21 Vy. Vy is 0. And so the velocity of the system after the collision is 0.2380 meters per second. But yes. From the x equation here, it's 5 divided by 21. Is that wrong? That's 21 divided by 5. Okay, so but notice that so that's one possible outcome of the collision with the ball and the kid. That's the one where he catches it. It's also possible that he would miss it and it would bounce off his forehead, and then the ball would bounce backwards and he would roll back the other way. So you have to know something about the collision to answer it. If we don't know that he catches it or don't know something specific about what happens when the ball comes to him, then we don't have enough information.